Okay, good day, grade 11s. Today we are going to be looking at questions that are based on Newton's first law. These type of questions generally come after the question in your exam paper on resultant forces and vectors. So let's dive straight into it. So this is question 3 of a November 28 exam paper, and it goes as follows. A box with a mass of 45 kgs is pulled with a force of 90 newtons at an angle of 50 degrees to the horizontal, and the box moves at constant velocity. All right. A very important piece of information here is that obviously our box is 45 kgs. So this box is going to have some weight that is acting downwards on the box. We also note that we have a 90 Newton force acting at an angle of 50 degrees. So we've got some force that is acting in this direction, which will have two components to it. It would have, if we call this force F, it will have the horizontal component, which we call Fx, and it would also have a vertical component, which we will call Fy. So we know that if we want to add or subtract forces acting on a point or from the center of mass of an object, we need to break them into their vertical and horizontal components, because we can only add and subtract collinear forces, forces that are acting on the same line. Another very important piece of information here is that the box is moving at constant velocity. Okay, what does that mean for us? Well, it means that the net force, F net, is going to be equal to 0 for this situation. Okay, so let's dive straight into the first question. With that being said, define the term kinetic frictional force. So we have two types of frictional forces that we are concerned with. The first is going to be your static frictional force, which is basically the frictional force that needs to be overcome in order to make an object start moving. So when an object is at rest, when an object is standing still and there are forces acting on it, there's a certain minimal force that needs to be overcome in order for that object to start moving. In this case, we are dealing with a box moving at constant velocity, hence the reason they have asked us to define the kinetic frictional force, which is the frictional force that basically opposes the motion of an object relative to its surface. So the exact definition would be the force that opposes the motion of an object relative to its surface. There you have it. Question 3.2 now says, state Newton's first law of motion in words. So they have actually gone and asked us to basically define two of our definitions in one go here, which is somewhat brutal for you guys. But Newton's first law of motion says that a body will remain in a state of rest or motion at constant velocity unless a non-zero resultant force or net force is acting upon it. Okay, so just bear in mind that whether this box is at rest or it is in constant motion or has constant velocity, our net force will remain to be 0. The box is not going to be accelerate unless that net force is greater than 0. Okay. Question 3.3 says, calculate the magnitude of the horizontal component of the applied force. Now, we love it when they do this for us. Basically, if you make a silly mistake on this question over here, you will likely lose those 2 marks, but we can continue marking with CA marks, or what do we call it? We call it positive marking. We can continue to mark you into the next question if you accidentally blunder in that first question. So we love it when they ask you to do this. We also love it when they ask you to draw a free body diagram, because I always recommend you draw free body diagrams for these types of situations, regardless of whether they ask you to do so or not. So what does our free body diagram look like? Well, we always start a free body diagram with a dot, which basically represents the center of mass of that object. Okay, that object has a mass, so it has a weight component which acts downwards. That is a W, not an N. We have some force that we know is going to be pulling the box. Okay, and it is pulling that box at 50 degrees to the horizontal. All right, if we have weight acting downwards and this box is sitting on a surface, we know that we are going to have a normal force which opposes that weight. It acts upwards in this case. Okay, and that force is necessary so that the box doesn't fall through the floor, basically, and our box is moving at constant velocity. Okay, and it's obviously moving to the right because that is the general direction of this force. So we know that we are going to have a frictional force which is kinetic in nature. Okay, it is kinetic frictional force opposing that motion, so it's going to be acting to the left. Okay, now just very quickly, this frictional force over here is equal to 90 newtons. Okay, and we can break this up into two components, namely Fx, and upwards we are going to have another force which we can call Fy. Okay, so the question 3.3 says calculate the magnitude of the horizontal component of the applied force. This is the applied force that's being applied to the box. Maybe it's someone pulling a string or something, who knows, but that is our applied force. And the horizontal component is going to be this Fx on the horizontal axis. So 3.3 basically looks like this. What we can do is we can actually draw a little triangle to help ourselves out here. So we've got F acting this way. Okay, we've got Fx, which is what we're interested in. Okay, and if it helps you, you can also shift your Fy. This Fy over here, you can shift it so that you form a triangle, and this helps you with the trig. This is a 90-degree angle over here now, and again, this is our 50 degrees over here. So we want to figure out what Fx is over here. So from that 50 degrees, what is this going to be? That is our adjacent side. F is our hypotenuse. So if you know your trig ratios, you know that Fx, okay, is going to be equal to F cos of theta. All right, where does that come from? Let me just show you quickly. Cos of theta is equal to the adjacent over the hypotenuse, which is Fx over F. I'm going to multiply both sides by F. And when I do that, basically what happens is this F comes over to this side and we get our equation. Okay, so Fx equals F cos theta. We can rewrite that as Fx is equal to 90, because that is our force, cos of 50 degrees. Okay, so we find Fx to be 57,85 newtons. Okay, and that is obviously acting to the right. There you have it. Okay, 3.4 now asks, okay, so question number 3.4 is asking us to calculate the magnitude of the normal force. So quickly going back to my free body diagram, the normal force is the force that is acting upwards over here. All right, because it's acting upwards, I am most likely going to be interested in what the weight is going to be and any other forces that might be acting directly up or down. And in this case, we can actually see that there is another force acting upwards. It is the vertical component of our applied force. Okay, very important to note that from your free body diagram. So, I mean, I could just draw another little free body diagram just in terms of our vertical forces, and you'll see that there are two forces acting upwards and one force acting downwards. Okay, so I can actually draw an equation from that, and what that looks like is basically the weight, because our net force is equal to 0. Okay, the weight that acts downwards must balance all of the forces that are acting upwards. So I can say that W is equal to the sum of those two upwards forces, which is going to be your normal force, and the Y component of your applied force. Okay, now what is the Y component of your applied force? Well, if we go back to our little triangle here for our applied force, this component here is opposite of our 50-degree angle, and our force itself is the hypotenuse. So we can say, I'll just do it over here in red, we can say that Fy is equal to F sine of theta. Okay, because if you remember your trig ratio, SOHCAHTOA, okay, we know that sine is your opposite over your hypotenuse, and we are dealing with the opposite and the hypotenuse over here. So I can take this right here and substitute it in to my Fy immediately. You could go and calculate it on the side first if you would like. That is perfectly fine. But for me, I prefer to write it like this. All right, so let's continue. Let's plug in all the information that we have. Okay, do we have W? Do we have weight? We do not have weight yet, but we can definitely find the weight. Okay, they told us it was 45 kgs. Now, what is the weight? Well, W is equal to mg, right? So W is going to be equal to that 45 kg mass, must be in kgs, multiplied by 9,8, which is the gravitational acceleration on Earth's surface. And we can go and plug that in there if we want. So even if I wanted to, I could already substitute this weight in like this if I want to. Okay, all I've done is where I see this W, I know it equals mg, and therefore I've just converted that W into that mg. And similar with my Fy, I've converted it into F sine theta. Okay, very useful techniques there. All right, so let's plug in our information. As we said, the mass was 45 kgs. Gravitational acceleration on Earth is 9,8. That is equal to our normal force, which is unknown at this point. Okay, F was equal to 90 if I'm not mistaken. So this is 90 sine 50 degrees. Okay, and now we can rearrange to solve for n. Okay, so n is going to be equal to, again, 45 multiplied by 9,8 minus 90 sine of 50. You can go and work these out individually if you want beforehand. You're more than welcome to do that. My recommendation, if you do that, is just save it in your calculator as A and as B, so that you have the long decimal strings that come with those numbers. But if you do it the way that I'm doing it here, there's no need to save anything, which is great. Okay, so we find our normal force to be equal to 372,06 newtons. All right, and that is obviously acting upward. There you have it. Okay, question 3.5 asks us to calculate the coefficient of kinetic friction. Okay, now, so the coefficient of kinetic friction is basically a value that we can relate the kinetic frictional force, all right, to the normal force. Okay, it is the ratio between two forces. So the coefficient of kinetic friction, which is associated with the symbol over here, which we call mu, okay, has no units, and it is less than 1, so it will be a fraction like 0.2 or 0.4, and it is completely dependent on the materials that the object and the surface are made of. So that could be plastic and metal, or wood and rubber. These will all have different coefficients of friction. This is mu k, so we're talking about kinetic friction, but you also get the coefficient of static friction, mu s, or mu s. Yeah, mu s is what we generally call it, and that is associated with the static frictional force. So nonetheless, let's quickly ask ourselves, can we find out what the frictional force is, and do we have the normal force? And yes, of course we have the normal force. So my question is, can we figure out what the kinetic frictional force is equal to? And we can, all right, along this horizontal over here, we only have two forces, okay, one acting left, one acting right. Because our F net is equal to 0, we know that they must be equal to each other. So we can say that Fk is equal to my horizontal component of my applied force, okay? So we know this to be true. And do we have this Fx? We 100% do. We calculated it earlier. It's 57.85 newtons, okay? So we can say that Fk is equal to 57.85 newtons, okay? And if you wanted to be more precise, you could say it's acting to the left. You could make this a negative value. All right, so let's quickly dive into this. We now know what Fk is, and we also know what the normal force is, okay? So if I rearrange this so that the coefficient of friction is the subject of my formula, I will find that it is equal to Fk divided by n, the normal force. So mu k, which is not going to be a negative value, it's going to be a positive value, is 57.85 divided by my normal force, which is 372.06. Remember how I said that this number is going to be less than 1. So my numerator is going to be larger than my denominator naturally. So my coefficient of kinetic friction is going to be equal to 0.16, and there are no units associated with this because it is the ratio between two forces. Okay, this is a Newton force and this is a Newton force, and in physics what you can in fact do is follow your units, so the units actually cancel out completely. Okay, so we have no units for our coefficient of kinetic friction. That was 3.5. Last but not least, number 3.6, we have, will the coefficient of kinetic friction change if the angle of the applied force is decreased? Write only yes or no and give a reason for your answer. Now, as I mentioned before, the coefficient of kinetic friction has to do with the type of materials which are in contact with each other. It has nothing to do with the angle at which our object is on an inclined plane, or the angle at which the applied force is pulling it, or anything like that. It is a constant, okay? The coefficient of kinetic friction and the coefficient of static friction, for that matter too, is always a constant depending on the types of materials. So the answer to this is going to be no, and that is your reason. Okay, so I hope this quick run through of this past paper question has helped you, and in the next episode or the next lesson we will dive into a slightly more challenging a question on this exact same topic. So enjoy. Peace.